Please welcome to the stage meeting co-chair Joshua Teen Pond.
Good evening, everyone. As a reminder, if you need closed captioning or translation to French, Canadian French, you can utilize the Wordly service in these general sessions, and the QR code is on the screen there. We've had an incredible and very busy week so far, but there's still more to come on Saturday as we wrap up the meeting. Don't miss the final general session and the closing ceremonies tomorrow morning after the breakout sessions in the morning. And also a reminder that if you are going to be around Montreal on Sunday, check out the website for more details about options for walking tours that are available around Montreal, and it looks like it's going to be a beautiful day, so it'd be a great day to see some of the city. And moving on with the program for the evening, here to introduce ASLO's John Martin Award winner is ASLO President Susanna Menden-Doyer.
Thank you, and before we get going with the award itself, I would like to acknowledge the awards subcommittee for the John Martin Award. Kite Siervogel is his chair, Soren Brothers, Andrea Garcia Bravo, Hans-Peter Grassert, and Isabelle Richer. I thank them profoundly, and I encourage you to consider nominating your colleagues and their amazing work for awards. ASLO has a broad range of awards for all career stages and efforts. The John Martin Award, established in 2005, recognizes a paper in aquatic sciences that is judged to have had a high impact on subsequent research in the field. The award is based on the 1991 publication by John Martin, Gordon, and Fitzwater in Limnology and Oceanography entitled "The Case for Iron," which argued the importance of iron limitation of phytoplankton productivity in vast areas of the ocean. This award is given to at most one paper per year. Unlike the Lindemann Award, which recognizes very recent papers within the last 2 years by early career investigators, the Martin Award is for papers that are at least 10 years old. The 2026 Martin Award is being presented for heterotrophic plasticity and resilience in bleached corals, for fundamentally altering our understanding of coral nutrition and resilience in an era of climate change, representing a true paradigm shift in coral reef ecology. Grottoli et al. Is the first paper to identify the trophic flexibility of corals as a survival mechanism, revealing a new perspective on coral feeding strategies and metabolic pathways. It is my pleasure to present the 2026 Martin Award to the paper's lead author, Dr. Andréa Grottoli, on behalf of all the co-authors, which include Lisa Rodriguez and James Pallardi.
Am I on? Yes, I can hear it. Well, thank you so much for having me here and for recognizing this paper. This is a picture of us at the time that we did this work. Jim Pallardi and Lisa Rodriguez were students of mine. Jim was an undergrad, Lisa was a grad student. I was 12 years old, and Lisa is now a full professor at Villanova, and Jim Pallardi is the Conservation Science Director at Pew Charitable Trusts. So thank you for recognizing this paper. I also want to point out that I started my path for corals in an indirect way right here at McGill. I was an undergraduate researcher in Rob Peters' lab at the same time as Paul Del Giorgio, who will be the next president of ASLO. And I was studying zooplankton, and little did I know then that I would still be looking at zooplankton all this time later. So coral reefs occupy less than 1% of the ocean, yet house 30% of all marine species, support tourism and jobs, protect shorelines from storms and erosion, and are essential for human well-being. Their annual economic value is estimated at close to $10 trillion globally. Corals are the building blocks of coral reefs. Yet, reefs are highly degraded because of ocean warming, ocean acidification, pollution, overfishing, and disease. And because of this, corals are in crisis, and warming is really the large global driver of a lot of their demise. At the current rate of warming, tropical surface ocean waters will warm by about 4 degrees Celsius, and all corals could die by 2050, even with some adaptation, according to some models. So, what can we do? Well, we definitely need to mitigate climate change. We need to decrease local stressors. We need to preserve what's still there, restore what has been lost. But this is a tall order in a world of constant climate change. And increasingly, we are recognizing that technological interventions are necessary to help bridge that gap to enhance restoration activities and conservation activities. My journey on all of this started with feeding corals for my PhD, and then it got jump-started with the Nature paper that is being recognized with the award today. So I'm going to walk you through a little bit of that paper and how it has led to where we are today. Corals are tropical, symbiotic, mixotrophic organisms. If we zoom in on this coral here up close, we see it's made up of polyps. They have tentacles. Those tentacles, they're an animal. They capture zooplankton and particulate organic matter and put it in their mouths. And when corals are healthy, they can get between 10 and 40% of their metabolic demand met. Are we okay? Okay. 10 to 40% of their metabolic demand can be met heterotrophically when they're healthy. If we dive down a little deeper, we see that inside of the animal cells are endosymbiotic algae. They photosynthesize far in excess of their own metabolic needs, translocate the vast majority of that fixed sugar to the coral host, and supply it with fuel. Healthy corals can get up to 100% of their metabolic demands met photosynthetically. But when seawater temperatures increase by as little as 1 to 2 degrees Celsius above thermal max for as little as 10 days, that symbiosis breaks down. The coral eject their endosymbiotic algae. We see through the clear gelatinous tissue of the animal host to the white skeleton underneath, hence the term bleaching. And this is a stressful condition because now they're not getting photosynthetically derived sugars. Corals that are bleached have low or no photosynthesis, so it's kind of a starvation mode. There's reduced coral health and increases in mortality. But what if feeding was a source of resilience? If you look at this picture on the bottom, let me see if I can get that. There's this one coral here. That's not the best, but you see the brown coral in that corner. Everything else is white, and one of them is brown. It's doing something different. There could be the endosymbiotic algae, it could be their microbiome, but it could be that they're good feeders. And so we've been digging into the role of coral feeding and coral resilience and how it helps them function in general. So we started with an experiment in Hawaii. This is Lisa Rodriguez and Jim Pilardi at the time. And we worked with Porites compressa, Montipora capitata that are shown here, Porites lobata. And half of the corals were put in tanks with heat, half not. At the end of the month, the heated tanks corals were bleached. The controls were nice and brown. They didn't have zooplankton in the tanks. Then we put them on the reef for 6 weeks. And of course, on the reef, there's zooplankton. And you can see that at the end of that 6 weeks, the Montiporas are still pretty pale. The Porites are starting to get a little brown, but they're still pale. And we said, okay, how are they doing? And then one of the first things we did is we quantified what proportion of metabolic demand is being met by photosynthesis alone. That's CSAR, it's a term muscatine developed in the 80s. And the red bars show that for Porites compressa, Porites lobata, and Montipora capitata, they're all meeting more than 100% of metabolic demand when they're healthy. But for the bleached corals, none of them were meeting 100% of metabolic demand. And what we did in this paper for the first time is we also quantified how much zooplankton they ate. So we put them out on the reef for an hour, we let them eat, and then we dissected the guts. And we counted how many zooplankton they ate, and we converted that into carbon units and developed this CHAR term, which is something that came out of this paper, and we said how much of their metabolic demand is being met by by eating zooplankton. And it's between 20 and 40% for the two Parietes species, whether they're bleached or not. But Montipora capitata dramatically increased its feeding rate and could meet 100% of metabolic demand when it was bleached. So when we add them together, we can see that all three species are meeting 100% of metabolic demand when they're bleached because of the amount that they're getting from feeding. So feeding enables bleached coral to meet metabolic demand. And what it also does is in corals that are heterotrophically plastic, like Montipora capitata, that goes from eating almost no zooplankton when it's healthy to only eating zooplankton, like a ton, when it's bleached, it can cope in all kinds of conditions because it has this flexibility. And that was one of the main things we found in this paper. But we also dug a little deeper to see, like, what are they doing with that extra carbon? And we measured some isotopes. And what this graph is showing is this heterotrophy index. And all you need to recognize is if it's a more negative number, which is a flipped axis here. So higher up on the graph means more heterotrophic, lower on the graph means less heterotrophic or more photoautotrophic. And once they were on the reef and they had access to zooplankton, those bleached corals had a lot more heterotrophic carbon getting into their tissues relative to the control. So we know that they're incorporating it into their tissues, and we measured the total energy reserves, lipid, protein, carbohydrate, all those together, and their biomass. And in Montipora capitata, we see that those bleached corals, once they have access to the zooplankton, recover their energy reserves and recover their biomass. We've pushed this a little farther, and we did some pulse chase isotope labeling experiments to track the carbon coming from photosynthesis and the carbon coming from eating zooplankton, and said, where is that going between the host, the endosymbiont, and the skeleton? So we can track these two lines of carbon acquisition. And I did this with my postdoc, Adam Hughes, that you can see in the background there with the hat. He hated having his picture taken. But we have several papers that came out of this. I'm gonna distill the first bit into this graphical representation, but understand there are about 3,000 stable isotope analyses that go into the next 3 slides. So on the left side, we have what happened to the carbon that came in photosynthetically in healthy corals. The photosynthetic pathway really is for meeting daily metabolic demand and calcification. So the corals are taking up DIC, CO2 from the water. The algae are taking that up for photosynthesis, translocating those sugars to the animal host. It gets respired. That respired carbon then ends up in the skeleton. Little bit gets recycled. On the feeding side, and I should back up and say that we know that it's being metabolized because the isotopic signature in that label decreased over time. So they weren't hanging on to that photosynthetic carbon, they were burning it and putting it in the skeleton. On the feeding side, that carbon was taken up by the animal host, but recycled between the host and the endosymbiotic algae. They were not burning that fuel, they were using it to build tissue. And we know this because the isotopic enrichment was the same in the host and the endosymbiont, and it stayed level for the whole week. So they weren't burning that fuel, and that's because heterotrophic carbon is nutrient rich. It's got vitamins, minerals, the whole periodic table. Photosynthetic carbon is sugar. Great fuel, you need fuel, but to grow tissue, to grow lipids, to reproduce, you need zooplankton. And that's one of the big things we found in this set of papers. But we followed this up, and we also did it with bleached corals. And so when corals are bleached, the whole photosynthetic side goes away, and we have way fewer endosymbiotic algae. The algae are there, sometimes aren't doing so great. And now the corals that are eating zooplankton, they're taking that up, and there's a net transfer, and I forgot to highlight in red that last arrow, of heterotrophically derived carbon going to the algae. In other words, the animal host is feeding the algae to help them recover. And this makes sense because a coral can't start calcifying until the algae and photosynthesis are back on board. And in Montipora capitata, that can take, and Parietes compressa, that can take 8 months or longer. So as long as the algae are not fully recovered, calcification is not coming on board. And we see evidence isotopically that the carbon that's coming from eating zooplankton, in this case labeled rotifers, was being net transferred to the endosymbiotic algae. They were more enriched isotopically than the host, even though the carbon was coming through the host. And then we did this again after 1 month of recovery, 4 months of recovery, and 11 months of recovery on the reef. And I'm only showing the results for the feeding side of this equation. On the left panel is Montipora capitata, on the right panel is Parietes compressa. And the way to read this graph is if the values, the circles, are above that very pale dashed line, I apologize for how pale it is, the pale dashed line at 0. If the value is above that, that means carbon assimilation by the bleached corals is greater than in the controls. And if the circle has a pi in it, it means it's significant. And what we found was that even 11 months later, in both species, the incorporation of heterotrophically derived carbon in bleached corals, far exceeded that of the controls. So the corals that looked recovered. 11 months later, they were brown, calcification was normal, lipids were normal, everything looked the same as the controls, but physiologically, they were not. Physiologically, the bleached corals were still doing something different than the controls. They were hoarding heterotrophically derived carbon. Maybe they're still recovering, maybe there's still cellular repair, or maybe they're hoarding in case there's another bleaching event. Either way, the impact of being bleached almost a year earlier persisted. And we see this also with lipids, so new lipid synthesis can be up to 80% heterotrophically derived even a year later in Parietes compressa, and between 60 and 80% in other cases. So there's this huge dependence on feeding in corals, even when they're not stressed, but they were. Okay, so coral feeding is a critical source of nutrition. It enables bleached corals to meet metabolic demand. It enables bleached corals to recover energy reserves and biomass. It's essential for tissue building and lipid synthesis. It's essential for long-term recovery. It minimizes heat stress impact and bleaching susceptibility. It's critical to survival at low pH, and it reduces mortality from heat stress. So this is a really important source of nutrition because of the complex nutrients and organic molecules that come with it. And I am selfishly only citing papers out of my lab on here, just to be transparent, but other people have done some work like this too. So if coral feeding is a critical source of nutrition, and we know that when they feed more, they're healthier, they grow more, and they survive more, and we know that coral feed more when you give them more to eat, how do we get them to eat more on the reef? And to do this, I've invented Uzella. Uzella is the Underwater Zooplankton Enhancement Light Array. It's an autonomous, programmable underwater light that's easy to deploy, requires minimal maintenance. It can operate for 6 months on a single battery, and it has a patent pending in 3 countries right now. And the way it works is you program it to turn on for an hour after sunset when zooplankton are migrating and when coral are known to feed. The light turns on, and zooplankton are phototactic. They're attracted to the light, and it attracts them down toward the light. And you can see in the cartoon, we point the light up so that the zooplankton come down to the coral that are surrounding it. That way, it locally concentrates zooplankton for coral so they have more feeding opportunities. We've tested this now in Hawaii. We are currently working on it in Florida and in the Red Sea, and I'm going to share with you some of our findings. So we first tested this in Hawaii with both healthy and bleached corals that we put on racks that you can see in that image, and we're going to swim by. This is in the coral nursery at the Hawaii Institute of Marine Biology, so it's underwater. And the racks had either bleached or non-bleached corals of our 2 favorite species, Montipora capitata and Parietes compressa. And the lights would turn on at night for 1 hour. And we had some racks with the lights and some racks without as controls. And you can see up close here, if we look, we can see kind of those speckles in the light. Those are the zooplankton coming to the light, toward the light, and giving corals more feeding opportunities. We wanted to make sure we were actually getting more zooplankton, so we quantified the zooplankton concentrations on the reef and on the controls, and those are the gray and the white bars, and there's across a bunch of different size classes and overall, and they're statistically the same. When we add Uzella, we get 4 to 7 times the concentration. And so it's working. It's locally concentrating like we hoped. After 10 days in that setup, we then harvested a subset of the corals, brought them into the lab, and dissected out their guts after they had fed and counted how much they ate. And for the ones that are either heat stress, the white bars, or the healthy controls, the gray bars, they ate between 0 and 3 zooplankton per 100 polyps. So we're literally at the microscope at midnight digging out the guts of 100 polyps on every frag and counting what they ate, because we want to make sure we know what they're eating. When we add Eusella, their feeding goes up by 10 to 50-fold. So having more food to eat lets them eat more. This is after 10 days. We repeated this at 6 months and at, I think, 3 months. But their enhanced feeding continued for the entire 6 months. By the end of 6 months, we see double the growth in the control corals that were given enhanced feeding with Eusella, but not with the bleached corals, because bleached corals only turn on calcification once they're fully recovered, especially in Montipora capitata. So it wasn't surprising that there was no enhanced calcification for the bleached ones, but there was for the controls. We also were wondering, well, maybe it's going to help with recruits. Recruits are really important for restoration because they're a source of new genetic variation, but they have high mortality rates. They're not really good photosynthesizers, but they really depend on zooplankton. And so Eusella could be a great tool for enhancing feeding in recruits and getting them to grow faster and out of that vulnerable phase. So we put some of these 3D clay printed domes that you see in that middle image in a tank, which are in the blue image, with Posilopera acuta while they were spawning, and then the larvae settled on the domes. The domes had those holes perforated into them, and a Eusella was put underneath. They were put out onto the reef for 6 months, and every night the Eusella would turn on. It would shine up through the holes. It looked like a disco ball. And at the end of the 6 months, we counted how many had survived and quantified their size. And I want to point out that the flat one there is the control, and then we had a smooth dome and a swirly dome version. And what we found was that after 6 months, none of them survived on the flat surface. There's too much exposure. And on the smooth and spiral dome, survivorship, which is on the left-hand panel, was similar in both of them, and growth was similar in both of them. But when we added Eusella, survivorship doubled, and growth quadrupled on the smooth dome and doubled on the spiral dome. So this is a dramatic change in survivorship and growth in these corals in a vulnerable phase. We are now continuing to study Eusella in 2 other scenarios, in Florida and the Coral Restoration Foundation's Tavernier Nursery, and in the Red Sea in collaboration with KAUST's Coral Restoration Initiative. Because this is going on YouTube, I'm not showing you any unpublished data, but I will tell you the punchline for what's in the pipeline. We have 1 paper in review and a couple papers in prep. And this work, I should point out too, is being led by a recent postdoc and PhD of mine, Anne-Marie Mihalver, Shannon Dixon, another grad student of mine, and Nick Wilson. So what we're learning is that Eusella increases growth. It can double it. It's between 30 and 100% increase in growth. Sometimes it's branch extension, sometimes it's total calcification, but we're seeing significant increases in growth. For Orbicella favulata, which is in the middle, it's a mounding coral with these little pieces that you grow when you're doing restoration. It offsets their winter skeletal loss, so they tend to lose skeleton in the winter, but with Eusella they don't, they keep growing. They're twice as likely to fuse with fragments that are nearby, which is a technique used for skinning and creating large coral colonies quickly. They are twice as, their zooplankton is incorporated in the tissues. We see isotopic evidence of that. We see evidence of photophysiological benefits based on several parameters made with a PAM measurement, and no evidence of negative light pollution effects based on some compound-specific lipid analyses using a marker that is known to indicate stress from light pollution. We see no evidence of stress from light pollution. So we have evidence that not only does Eusella help feeding and growth and survivorship, but it doesn't seem to have any negative effects that we can detect so far on the coral's biology. We think this can be really useful for restoration in nonprofits or government organizations. It was originally developed as part of a DARPA project for a hybrid reef, which is that first top left-hand image, a artificial reef where you make concrete structures and glue corals to it so it can self-sustain, and Eusella was part of that to ensure the corals could grow. It could be used scientifically. Governments, private resorts, they often have their own reefs, or they have ecotourism things. We could incorporate it into that. Either way, in order to scale up, we need a manufacturable version. The picture I showed you earlier, the prototype, that was handmade. My grad student was soldering the board, that kind of thing. We used off-the-shelf PVC pipe, but that is not how you can scale. So we had a grant from the state of Ohio to work with an engineering and manufacturing company in Ohio to build a manufacturable version of Uzella. And this is it. It is, now includes a user-friendly software interface. It has flexible light programming, so you can make it go every other night, once a week, every 3 days, whatever you want. Half-hour, hour, 2-hour illumination. It has maximum flexibility. It's half the size. It still requires maintenance every 6 months, but it now has rechargeable batteries, and it has versatile attachment features. So I'm gonna just spin it. The light is on in the left-hand panel there, and it's on a spinning disc, so you can kind of see it from multiple sides. And then it has a removable magnetic wiper. So our previous version, someone had to go out there and wipe the lens. That is not very scalable. It now has a wiper. So it's actually the wiper that's moving in that video. It's not the table underneath it. And I stopped the video, but it does do the full way around. And it's an S shape because it helps slough material off. We tried a straight blade and it didn't work as well, but the S shape helps slough the material off. And our future designs, we have just launched the company, and if the company succeeds, the goal is within the next 3 years to create Uzella Plus, which will integrate a PAR sensor and a temperature logger, since those are measurements that are being made in restoration all the time anyway. And with the integrated wiper, you would have high quality downwelling light irradiance data. We are also investigating from a scientific perspective how Uzella could be helpful and how we can better understand corals themselves. So does Uzella enhance rammet outplant success? We've worked with them in nurseries, but we haven't outplanted them to the reef with the corals when they get outplanted for restoration. We have a pilot project this summer with our collaborators at CRF in Florida to test that. We want to know, do reefs with higher zooplankton density foster higher recruitment, health, and survivorship? And is there an effect on the community composition of the non-coral benthic community? And we have a proposal pending with NSF in collaboration with Aaron Mueller and Josh Maiden to tackle that question. And then we want to know, does Uzella minimize bleaching susceptibility or enhance recovery? It turns out for us to really test this, because Uzella leverages natural zooplankton, and it's impossible to get enough zooplankton in a tank to do it in an artificial setting, we have to wait for a natural bleaching event to occur while we're already running an experiment to test that. And the way things are going, we'll probably get our wish. And we're commercializing. So in order to get Uzella out there and people to use it, we need to be able to scale up. We have registered the company. I have a CEO and a CMO. We have a website that looks like this. You're welcome to visit it. It says we have a newsletter, but literally this website went live last week. But we are scaling up. We've written a grant to the state of Ohio to manufacture and to get molds and work with the same engineering and manufacturing company to manufacture the first set and to start testing at scale and collaborating at scale and selling at scale. Our long-term vision is to have a program where some of the older Uzellas get exchanged back and we can refurbish them and sell them at a discounted price, and for people that are in low-income countries so that they can be more broadly used. And there's a real economic reality to this. The Uzella optimizes already very large investments. There are over 900 restoration programs in the world, and at enormous cost. If Uzella decreases your nursery time by 6 months, that's a massive return on investment for using the device. And we know that restoration has a 1.2 to 1.4 return on local economic investment. It is a better return than building a hospital. So there are a lot of economic incentives for communities, coastal communities, states, cities to invest in reef restoration, and there's also an economic benefit to doing that, and Uzella could be part of that. So feeding corals can be part of the solution, and it is likely to increase coral restoration and conservation efficacy and success, and Uzella may be part of that. And what started as an interest in coral feeding as a pathway for coral resilience developed into a technological solution that could have a positive impact on coral restoration success. I did not do this alone. There's an army of people that have been working with me. On the left-hand side is my Ohio State team, and it does not include most of the undergrads. I've had over 100 undergrads work in my lab. Many of them have come in the field. Some are co-authors. I have my UZELA team. I have other collaborators that were part of those earlier studies, and now we're working with several teams testing UZELA globally, in Florida with CRF, in Hawaii with the HIMB team, and in the Red Sea with the COUS team. Thank you so much. And I have 3.5 minutes left. Anybody has any questions? Yeah, I think there's a mic right there if you want to go up to the mic.
It's work. Yeah.
Yeah.
Thank you very much. That's really interesting to see like how you integrate acidification, DAC, and everything. And I was wondering in your isotope results with carbons, how you consider DBL, diffuse boundary layer, and if you had like a fixed flow rate for your experiments.
Mm-hmm. Yeah, so when we did the pulse chase isotope labeling, we had flow in the tanks because you need to have flow or you get too thick of a boundary layer. So we did do that. We, as best as we could under those conditions, but whenever we've done other isotope natural abundance stuff, it's on the reef. So it's all natural conditions, and what we find in natural conditions is consistent with what we found with those tank-based experiments, so we think we did okay.
It's interesting, thank you.
Yeah.
Hello, thank you for this very interesting talk.
Thanks.
So I wonder, if you apply UZELA in the open ocean, in the reefs, have you looked, or are there any possible negative consequences on the local zooplankton community, that they maybe after some time, they may not reproduce so much anymore, and then the reefs also don't have enough food? Yeah.
So that's a great question. There are two parts to that. One, the lights are only on for an hour or less. It's a very short period of time, and what it's doing is it's taking the zooplankton that might be in about a half-meter dome over the light and compressing it down. It's not stealing zooplankton from over here. They're not moving side by side. That's why the controls were no different than the reef. So there's that. The coral are going from eating 0 to 3 zooplankton per 100 polyps to 12 to 20 per 100 polyps. So it's a lot for coral, but it's in the noise level of zooplankton concentrations when we calculate them. So I think what's a bigger threat to the zooplankton abundance is climate change, because there's some evidence that as the oceans are getting warmer, that abundance is going down. I don't know that corals are going to do more damage than that. But it's a fair question, yeah.
Hi, thanks for that good news story. It's nice to hear them from time to time. I was wondering if you know or have any ideas if there's any maybe positive impacts on fish recruitment, larval fish recruitment from these kind of light traps. Do you have any evidence or ideas about how that might be affected?
Yeah, I mean, certainly lights attract little fish. We see them come in, it attracts all kinds of stuff. I would love if a giant manta ray just showed up too. I'm just praying, because they like that too. We don't. It's too close to shore. But we don't know. So this proposal we have with NSF would assess fish communities above the racks that have UZELA and the ones that don't, to address those questions exactly. Is it affecting fish communities? Is it affecting the benthic community? Because we're changing the zooplankton dynamic above that little mini ecosystem we've created on the rack with the UZELAs. So we'll see. My initial gut feeling is, I don't think so, because it's short, like it's an hour a night, and I think in a lot of cases it's not going to be for the whole year. It might be parts of the year or more vulnerable parts of the year. It might be in the winter that you do it to fatten them up before heat stress. It might be during heat stress. It might be during recovery, but I don't know that it'll necessarily be year-round. And I should point out that UZELA is a technological solution that can be used to help some corals in some places sometimes. But it's not like you're going to light up the whole Great Barrier Reef with UZELA. It's not cost-effective. It's not practical. It's not meant for that scale. It's meant for the scale of restoration of hectares at a time. And on that scale, I think it can be effective. And when you're implementing it, it's because things are already really bad. And so between maybe some negative effects of UZELA and no reef at all, then the choices become a little more binary. But you wouldn't put it on a healthy reef necessarily, if such a thing exists. I'm at time. Thank you so much.